And welcome back to a video lecture. This one introducing the concept of equilibrium in chemical reactions. So homogeneous reactions take place within the liquid phase. If the reactions are reversible and proceed rapidly, there is a local chemical equilibrium, right? So if the reaction is not at equilibrium or is not reversible, then they are homogeneous non-equilibrium reaction. Meaning an equilibrium is essentially something that is reached if things go fast and you end up with a steady state essentially reaction. So imagine here you have a simple mixture of iodide and hydrogen, right? They separate and they end up at equilibrium where the reaction rates are the same essentially for the forward and the reverse reaction. So K1 and K2 here are the same. So everything is at equilibrium. So there's a constant amount of the products and reactants in the solution that basically there's no net change in the amounts. So again, there's a rate to the right, K1, and we'll do a little bit more kinetics in the next lecture, but here I'm just introducing this important concept of equilibrium. So if there's a rate to the right, A plus B go at a rate K1 to C, and then to the left, C can separate into A and B at a rate K2. If K1 and K2 are 0, the reaction, if K1 or K2 is 0, then the reaction is obviously irreversible. Otherwise, there is an equilibrium constant, right, that we can define as the ratio of the rates, right, or the ratio of the products divided by the product of the reactants, right, C divided by A times B in this case. So if the reaction rates are fast relative to transport rates, then the equilibrium may be achieved in a short period. Now, environmental systems are open systems typically, right, and they're away from actual equilibrium. So oftentimes, concentrations are maintained in environmental systems at the boundaries, meaning if there's a flux in, right, if there's an overwhelming flux of something, right, then the amount of this thing may not be affected much by the reactions within the system, but by the flux at the boundaries, right? So an example is, let's say, photosynthesis, right? If there's a flux of photons and carbon dioxide from the atmosphere, right, that is continuously reduced by the plant into sugar, right, there's really no equilibrium to speak of because everything is, flux at the boundary essentially. So there is, we're basically a pseudo equilibrium, or there's some, we're away from, it's a non-equilibrium. We maintain that non-equilibrium basically because there's a flux of energy through the system. Now, if we add the stoichiometric coefficient, so let's say AA plus BB gives CC, right? The equilibrium constant, and I'm sorry this is a little small here, but hopefully we can still see it. The equilibrium constant is now, the concentration of the product C to the power of its stoichiometric coefficient, okay? So this we already discussed, but here is the important figure where, the rates at equilibrium become the same. So at equilibrium, everything is at equilibrium, so there's no net change. So here's the other important aspect, that we have some amount of reactants and some amount of products, right? And at steady state or at equilibrium, again, equilibrium, you can think of it as a steady state. The net change doesn't exist. So those reactions still proceed, but there's as much, to the left, to the right. So then there's no net change of, reactants or products. And again, the rates to the left and to the right are the same. And this is really the main, the main point about equilibrium. So think of equilibrium almost as a steady state that we've described before when dc/dt equals 0. Okay, thank you. In the next lecture, I will talk about kinetics a little more, right? Those rates of reactions. Thank you.